Welcome to The Explainer. Okay, today we're embarking on this completely immersive, high-speed journey into literally the most extreme, mind-bending gravitational physics in the known universe. We're going to explore the cutting-edge science of what actually happens when the very fabric of space and time collapses in on itself. Now, I want you to hook into this thought experiment with me right now. Imagine strapping yourself into a highly advanced spaceship. We're firing the thrusters and we are setting a direct, undeniable collision course with a black hole. So what exactly happens? To your body, your perception of time, and, well, the very information that makes up your reality as you fall into the abyss. Okay, let's dive right into this. To ground our journey in reality, let's look at the supermassive black hole at the center of the M87 galaxy. What you're seeing isn't the black hole itself, because, black holes trap all light, but rather the intensely glowing accretion disk. It's this ring of superheated gas and matter violently orbiting a dark central shadow. And that dark shadow, that is our destination. But to really understand what we're diving into, we have to grasp the absolutely absurd density of these objects. Let's say you wanted to artificially create a black hole out of our sun. You couldn't just leave it as is. You would have to take the entire mass of our star and violently squash it down, and squash it, and squash it, until its radius was a tiny, microscopic 3 kilometers. Just 3 kilometers. At that point, the gravity at its surface becomes so immense that the escape velocity actually exceeds the speed of light. But hey, we aren't stopping at some small stellar mass black hole. Let's really ramp up the scale. We're heading to Sagittarius A star, the supermassive black hole sitting right at the center of our own Milky Way galaxy. By observing the warped movement of stars orbiting empty space, scientists know this absolute behemoth has a mass of 4.3 million times that of our sun. Let that sink in. So, as our ship approaches, we shut off the engines and enter freefall. We're now approaching the event horizon. This is it. The absolute point of no return. You can kind of think of the event horizon not just as a static boundary, but as a place where the literal river of spacetime itself is flowing inward. Right at the horizon, space is flowing into the sinkhole exactly at the speed of light. Once you cross it, space is flowing inward faster than light itself. But here is where Einstein's general relativity completely splits our reality in two. As we cross this boundary, severe gravitational time dilation creates this terrifying dual reality. For you and me, inside the ship, we just fall straight through. No big deal. But for an outside observer, say watching us through a powerful telescope from Earth, they witness something completely different. To them, we literally start moving in slow motion. As physicist Brian Cox noted, they would see our time stop on the horizon. An external observer never actually sees you fall in. From their perspective, the gravitational field is so incredibly intense that the light climbing out to reach their telescope is stripped of its energy. It becomes infinitely redshifted. So from a mathematical standpoint, time for you simply grinds to an absolute halt. To the outside universe, you just become this frozen, fading red ghost plastered on the edge of the abyss for eternity. Wild, right? But inside the ship, time feels completely normal. Unfortunately for us, though, physics is about to exact a brutal toll. We're about to experience something called spaghettification. Because gravity acts on a gradient, the gravitational pull on the bottom of our spaceship, or, the feet of your spacesuit, is significantly stronger than the pull on your head. The late Stephen Hawking famously coined this rather macabre term, describing how an infalling astronaut would literally be stretched like spaghetti. Extreme tidal forces would stretch you vertically while simultaneously compressing you horizontally, just pulling your left and right sides inward. It's this gruesome noodle effect that literally no physical material can withstand. But here's a highly counterintuitive and, frankly, absolutely fascinating fact. Falling into a supermassive black hole like Sagittarius A star is actually safer initially. Crazy, I know. For a massive black hole, the event horizon is so unbelievably huge that the tidal forces at the boundary are actually relatively weak. You'd cross the horizon without even noticing. The spaghettification happens much deeper inside. But for a smaller stellar mass black hole, the space-time curvature is so sharp that you'd be torn to shreds before you even reach the event horizon. So, since we chose the supermassive route, we cross the horizon intact, only to be crushed later. But what are we actually falling toward? What awaits at the very center of this gravitational well? Well, we're falling toward the singularity, And this brilliantly illustrates the problem. At this point, the mathematics of space-time just completely break down. They spiral toward absolute infinity. But the singularity isn't really a place in space. Because space-time is so distorted here, the singularity becomes a moment in time. It is literally the end of time. Trying to avoid the singularity once you're inside a black hole is a lot like trying to run away from tomorrow. It's inescapable, simply because it exists in your absolute future. So our journey essentially ends at the singularity, a fundamental breaking point in reality. But let's zoom out for a second to the macrocosmic scale. Is this gravitational tomb truly permanent? Do black holes just sit in the universe forever, getting larger and larger as they consume matter? Well, according to classical physics, yeah, they do. But in 1974, Stephen Hawking introduced quantum mechanics to the equation and discovered something totally astounding. Black holes aren't exactly black. They actually emit a very faint thermal glow known as Hawking radiation. And because they're emitting energy, they're slowly losing mass. Given enough eons, a black hole will eventually evaporate entirely. Which brings us to the ultimate cliffhanger in modern physics, the information paradox. Think about it. If we fall into a black hole, our quantum information is trapped inside, right? But if the black hole eventually evaporates into random, featureless thermal radiation, what happens to our data? The most fundamental laws of quantum mechanics strictly state that information cannot be destroyed. So where does it go? Well, there's a cutting-edge physics model, actually projected for publication in 2026, that proposes a totally wild solution. It drops the concept of the singularity entirely. The theory suggests that at the microscopic Planck scale, a property called torsion generates this repulsive force that literally halts gravitational collapse. So instead of evaporating into nothingness, the evaporation stops right at the end, and it leaves behind a stable, finite-sized, 7-dimensional wormhole structure. No way, right? So the crucial point is this. The black hole doesn't disappear. It leaves a remnant. And this remnant acts as basically an eternal hard drive for the entire universe. The 2026 calculations reveal that just a single solar mass black hole remnant could store approximately 1.551 times 10 to the 77th power qubits of information. To put that into perspective for you, that is vastly more data than there are atoms in the observable universe. It encodes literally everything that ever fell in, storing it through long-lived quantum vibrations within its 7-dimensional geometry. But what's even more staggering is the actual size of these leftover fragments. These Planckian relics would have a mass of roughly 9 times 10 to the negative 41st kilograms. That's a weight so unimaginably microscopic it makes an electron look like a giant boulder. They are virtually invisible, yet entirely stable, and just scattered throughout the cosmos. In fact, physicists are now theorizing that these invisible, information-packed remnants might actually be the mysterious dark matter that holds our entire universe together. So, from a supermassive beast crushing entire stars to a 7-dimensional microscopic wormhole holding the quantum memory of the universe, it's a lot to take in. If this model holds true, black holes aren't the end of space and time at all. They are literally the key to its underlying structure. So I want to leave you with this to ponder. If the deepest, darkest pits of the cosmos are just doorways to other higher dimensions, where does our reality actually begin? Think about that for a bit, and I'll catch you in the next explainer.